On behalf of 24houranswers.com, I welcome you to today's lesson. In this video, we're going to talk about the second derivative and concavity of a rational function, and this will be part one of a probably part two series on discussing the second derivative and concavity. In previous videos, we have been working with this function quite a bit. We have found the critical values of the rational function. We have also found the intervals of increasing and decreasing of this same function. And then we talked about the relative maxima and minima of this rational function. And each video is broken up into parts so that you can build up to this point now where we're going to talk about the second derivative. If you've been following along, we have this first derivative that we use back to find the critical values. Let's simplify this up and let's find the second derivative of this rational function, and then we're going to work a little bit more with it as well. So to clean this up, I'm going to distribute the 2x to these terms here. So 2x times 2x is 4x squared. Taking that 2x, multiplying it by 3, we have plus 6x. Let's distribute this negative 2 to the x squared. We have negative 2x squared. And then negative 2 times a negative 2 gives us positive 4. And all this is going to be over 2x plus 3 squared. Now I'm going to leave that alone for right now. Let's combine like terms in our numerator. We have 2x squared plus 6x plus 4, all over our same denominator. So this is our first derivative here, and we could do some simplifying with this, but honestly it's not going to make a difference. Nothing's going to cancel out. And what I want to go ahead and do now is proceed with finding the second derivative now. So f double prime of x. We have to apply the quotient rule again. So the quotient rule, the way we discussed it back when we found the critical numbers, is we do low. That means we leave the bottom function alone, 2x plus 3 squared. D high, we find the derivative of the top function, which is going to be 4x plus 6 minus high. That means we leave the high function alone, the top function. D low, we take the derivative of the bottom function, and I'm going to make a little bit of room here. So what is the derivative of this low function? You could square this binomial and then find its derivative, or you could apply the chain rule. Either way, it's going to work out just fine. What I'm going to do is apply the chain rule. I'm going to pull my 2 down, leave the inside alone. Remember to subtract 1 from our exponent. I'm applying the chain rule, so that's to the first power. And then we come back and multiply by the derivative of the inside, so that's going to be another 2 there as well. And then we put this all over low. Low means we take this function and we square it. So it's going to be 2x plus 3 squared, and then the entire thing is getting squared again. I know that looks crazy, but we can actually avoid all of that stuff at the bottom right here in a moment. So let's double check this. This was our first derivative, and we took low right there, d high, the derivative of the top, that's that right there, minus high, we leave the top function alone, d low, that's the derivative of the bottom, we took that right there and applied the chain rule, and this is all over low, or bottom squared. We took the bottom function right there, and then we squared it. Now, what are we going to do with this second derivative? We want to take this second derivative and set it equal to 0. This is going to help us determine concavity. Well, this is going to be tedious to simplify out, but what we want to do here is take the 2x plus 3 and square it. 2x plus 3 all squared gives us this part here. Now let's bring down our 4x plus 6, bring down our minus. And what I'm going to do here is I'm going to take this 2 times this 2, and I'm going to go ahead and distribute it to here. It doesn't really matter how you handle this, but we got a lot of multiplying to do with all of this. And I'll explain why I'm multiplying everything out in a moment. It's actually going to help us solve this equation since we're setting it equal to 0. But again, taking 2 times 2 and distributing that to the 2x, that's going to give us 8x, because 2 times 2 is 4, times that 2 is 8. And then 2 times 2 is 4, times that 3 gives us 12 there. But I have not touched this trinomial right here yet, so I'm going to bring it on down. And this is all over that low. But we can write that as 2x plus 3 to the 4th power. Now, I mentioned a moment ago, this looks crazy. We can actually not even worry about this because the only time a fraction, this crazy looking fraction, the only time this thing can be equal to 0 is when the numerator is equal to 0. And really what you can do algebraically is we can multiply both sides by 2x plus 3 to the fourth. This step is really not necessary if you understood what I said just before doing this. The only time a fraction can be equal to 0 is when the numerator is equal to 0. So really we can just throw this thing away, but algebraically what are we doing? We're multiplying both sides by 2x plus 3 to the fourth. That cancels out the 2x plus 3 to the fourth over here, and 0 times that stuff is still going to be 0. So therefore we have 0 is equal to this entire numerator. Now let's work on multiplying this numerator out, combining like terms, and simplifying it down to something that we can solve. Therefore, working on this trinomial and this binomial, 4x squared times 4x is 16x to the third power. 4x squared times 6 is plus 24x squared. 12x times 4x, 48x squared. 12x times 6, 72x. 9 times 4x, positive 36x, and 9 times 6 is 54. Now that is just the first part of our numerator. Now we have to come in here and work on the second part. Now to avoid too much confusion here, and I'm just going to put the minus, and we're going to subtract whatever we get when we multiply these things together. So we're going to have to change some signs. You could handle the negative right now if you wanted to, but I'm just going to wait on that. I'm going to take that 8x times that 2x squared, that's going to be 16x cubed. 8x times 6x, that's plus 48x squared. 8x times 4, that's plus 32x. 12 times 2x squared, that's 24x squared. And making just a little bit more room here, 12 times that 6x, that's plus 72x. And then finally 12 times 4 is 48. Luckily, what we have going on here is we are going to have some things that cancel out. Notice we have 16x cubed minus 16x cubed, so those cancel out. Let's keep on going and see what else happens. 48x squared minus 48x squared, so those cancel out as well. Let's see what else we get. 24x squared minus 24x squared. See you later. So this is working out quite nice, right? 72x minus 72x, those cancel out. 36x minus 32x. You see that right there? 36x minus 32x, so we get 4x. And then we have 54 minus 48, that gives us a positive 6. So what we want to do here is we want to set this equal to 0, which is what I've done here. Setting this equal to 0, we subtract 6 and divide by 4. We have negative 6 over 4 is equal to x. Well, that's the same thing as x is equal to negative 3 halves. All of this work just to get something that we already knew. This does not always happen with rational functions, but in this case it's going to. Negative 3 halves was actually a vertical asymptote of the original function. If we were to plug in negative 3 halves into the denominator of the original function, if you recall, if you've watched the previous videos, we have talked about that quite a bit. That's a spot where the function is not defined. It turns out that's a spot where the derivative's not defined. As a matter of fact, it's a spot where the second derivative's not defined. So this is the only value of x that makes our second derivative equal to 0. So therefore, we already knew x equals negative 3 halves was something that was going to influence our second derivative, so to speak. So our second derivative is equal to 0 when x is equal to negative 3 halves, but it turns out our second derivative is undefined when x is equal to negative 3 halves, because up here, or before I even canceled out, negative 3 halves is something that makes our denominator equal to 0. So in part 2, when we come back and look at this, we're going to create another number chart. We're going to create some test values, and we're going to test the second derivative both on the left-hand side of negative 3 halves and the right-hand side of negative 3 halves. And that's where we finally can come to some conclusions about the concavity of this rational function. And there you have it, a rather long and tedious problem, only to come to the conclusion that this value of x was actually a value of x that made the second derivative undefined. As mentioned earlier, it made the first derivative undefined as well, and the original function. Do not always count on that happening. Sometimes when you find the second derivative and you set it equal to 0, you will get some values of x where the second derivative is really equal to 0 versus where it's undefined. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.